When word spread that NASA had tested an engine that could run without fuel, the scientific world stopped cold.
This is no ordinary rocket engine, with NASA's revolutionary test of this rotating detonation engine.
If the data was real, it meant a machine had just moved without anything to push against, a direct violation of Newton's laws. Inside NASA's lab, sensors recorded a faint, steady force that shouldn't exist. It wasn't noise or error, it was real motion. Now the question is, what did they really find and why is no one at NASA talking about it? The day NASA challenged physics. In 2016, the world stopped in disbelief when headlines exploded across the internet claiming that NASA had done the impossible. Videos, podcasts, and news anchors repeated the same terrifying line. NASA just tested an engine that breaks the laws of physics. The story sounded like something pulled from a science fiction nightmare, yet it was real. Inside a small, heavily guarded lab at NASA's Johnson Space Center in Houston, a handful of engineers had quietly tested a strange metallic device that seemed to do what every scientist said could never happen. It moved without fuel. The device came from NASA's EagleWorks laboratories, a research group known for testing the limits of physics. Their goal was to explore experimental propulsion concepts that could someday change how we travel through space. When their early readings showed that this new thruster produced a faint push, it caused panic among scientists who understood what that meant. For centuries, all motion has depended on a simple rule called Newton's third law of motion. The law states that every action must have an equal and opposite reaction. If a rocket wants to move forward, it must throw something backward, usually fire, gas, or particles. That rule governs every car, jet, and rocket ever built. But this strange NASA device was different. It moved without throwing anything back. The readings were small but undeniable. The team detected thrust in the micro-Newton range, far too weak to lift even a sheet of paper, but strong enough to rise above the background noise of the lab's instruments. For scientists, that was a disturbing sign. If the reading was correct, it meant something in our understanding of motion was incomplete. Either the equipment was wrong, or the universe itself was hiding a loophole in its most trusted law. When NASA published the results in a peer-reviewed journal, the scientific world erupted. Some called it a revolution, others called it a disaster for physics. The agency's engineers insisted they had not discovered new physics, only strange data that needed explaining. But outside the lab, no one cared about the careful disclaimers. To the public, NASA had just broken the rules that hold the universe together. What made the situation even more intense was that the results came at a time when space agencies were desperate for breakthroughs. Chemical rockets were expensive, slow, and limited. If the strange NASA thruster truly worked, it could end the age of fuel-based propulsion forever. It could mean ships that never stop accelerating, probes that never run out of power, and travel across the solar system without refueling. The hope was blinding, but the fear was worse, because if the readings were real, then the very foundation of physics might have been wrong all along. Inside NASA, curiosity turned into obsession. The engineers rechecked every wire, every sensor, and every temperature shift in the lab. Nothing fully explained the anomaly. The more they searched for an error, the more questions appeared. Could there be an invisible reaction happening in space itself? Was there a property of the vacuum that could push back? From the EmDrive to the helical engine. It started in 2001 inside a small workshop near Guildford, England. There, a British engineer named Roger Scheuer built something that would shake the scientific world. He called it the EmDrive, short for electromagnetic drive. Scheuer claimed it could generate thrust without fuel. To many physicists, that sounded insane. But Scheuer believed his design was real. The EmDrive was shaped like a metal cone with one end wider than the other. Inside this sealed cavity, microwaves would bounce back and forth. The idea was that the energy waves would push harder on one end of the cone than the other, creating forward movement. To an untrained eye, it looked simple, but to a physicist, it looked impossible. The device had no exhaust, no propellant, and no clear way to push against anything. According to every physics textbook, such a thing could not move at all. Scheuer's early tests seemed to show a small amount of thrust. His instruments detected minute movements that he claimed were proof of a new kind of propulsion. But critics tore into his work. They argued that what he was measuring wasn't thrust, but thermal expansion, which are tiny shifts caused by the metal heating up. Others said it was electromagnetic interference. The numbers were real, but the cause was unclear. Still, the idea refused to die. By 2008, Chinese researchers built their own EmDrive. They reported similar results, a very small but measurable force. The Chinese Academy of Space Technology even hinted that it had tested the device in space, though no official data ever confirmed this. Western scientists laughed, yet they kept watching. If the EmDrive worked, it could mean spacecraft that never needed to refuel. The possibility was too important to ignore. In 2013, Dr. Harold Sonny White, a physicist at NASA's EagleWorks laboratories, decided to test it himself. His team built a new version of Scheuer's cone using advanced vacuum chambers and laser measurement tools. The readings again showed tiny thrusts, measured in micronewtons. White was cautious. He refused to call it proof, but admitted the data was strange enough to demand more research. NASA's involvement reignited the world's curiosity. If one of the most advanced space agencies on Earth was testing it, then perhaps there was something more to it than error. Still, the mystery deepened. Every test brought the same question. If no mass was being expelled, what was pushing the device forward? Some suspected electromagnetic contact with the lab environment. Others whispered about unknown quantum forces. Most physicists dismissed it completely, calling it a waste of time. But in 2019, one NASA engineer took the idea in a new direction. Dr. David Burns, working at NASA's Marshall Space Flight Center, introduced something far stranger. His concept, called the helical engine, did not rely on microwaves or magnetic fields. It used Einstein's theory of special relativity. Their relativistic mass no fewer breaking down the science. Imagine a machine the size of a skyscraper, shaped like a giant metal spring coiled in endless loops. Inside this spiral chamber, streams of charged particles called ions race through magnetic tunnels at incredible speeds. This is the basic vision of Dr. David Burns's helical engine, a propulsion system designed to function entirely in the vacuum of space. Instead of burning fuel, it would rely on movement itself. The engine's core idea is rooted in Einstein's theory of special relativity, which says that as an object moves faster and approaches the speed of light, its mass increases. Burns believed this effect could be harnessed to generate thrust. Inside his theoretical design, ions would be accelerated around the helical coil until they reached near-light velocity. As they move faster, they become slightly heavier. When they are redirected back along the loop, the change in their mass creates an imbalance. The heavier ions on one side would hit the turning point with greater momentum than the lighter ions returning, creating a very small but constant forward push. To make this easier to picture, Burns used a simple analogy. Imagine a spring-loaded ring bouncing back and forth inside a box. At normal speeds, the box barely moves because the forces inside cancel out. But if the ring were somehow able to move close to light speed, its mass would increase dramatically. Each time it slammed into the wall of the box, the heavier impact would nudge the box forward. Over time, those small nudges could add up to real motion. The helical engine applies that same principle, not with a ring but with streams of accelerated ions. However, this elegant concept demands staggering engineering. The ion accelerators would need to operate continuously at near-relativistic speeds, which means reaching over 90% of light velocity. To power this, Burns estimated a requirement of about 165 megawatts, roughly equal to the output of a nuclear submarine reactor. The system could only work in deep space, where there is no air resistance or friction to interfere with the delicate ion flow. Even the smallest drag or environmental disturbance could disrupt the precise balance needed for thrust. Burns himself admitted that his model remains entirely theoretical. It exists only as a mathematical framework built on relativistic equations rather than test data. His calculations do not violate Einstein's laws, which is what makes the idea so fascinating. In theory, the helical engine could work. In practice, we lack the technology to build or test it. The machinery would need to be over 200 meters long, with magnetic fields stable enough to control ions moving at near light speed. For now, that level of engineering remains out of reach. Still, NASA's internal review found the concept intriguing because it did not break physics. It stretched the rules but did not destroy them. That subtle distinction was enough to keep the idea alive. After all, history is filled with breakthroughs that began as mathematical fantasies. Airplanes, radios, and even nuclear power were once dismissed as impossible until technology caught up. Yet for every daring theory, the physics community had a single question: how can you move forward without pushing backward? That challenge turned excitement into fierce skepticism. Why scientists refused to believe it? From the beginning, physicists had one uncompromising rule: no thrust is possible without pushing something in the opposite direction. This is the law of conservation of momentum, a principle so fundamental that it governs every rocket, satellite, and atom ever observed. As one physicist put it, you can't get thrust without reaction mass. That statement became the battle line between belief and disbelief. When NASA's EagleWorks team first claimed the EmDrive produced measurable thrust, German scientist Martin Tajmar decided to investigate under stricter laboratory conditions. Tajmar, known for his work on satellite propulsion, replicated the setup in 2018 using sensitive magnetic shielding. His results were devastating to enthusiasts. The tiny forces others thought they detected were not thrust at all, but illusions created by Earth's magnetic field interacting with the power cables. The current running through the device induced minute vibrations that instruments misread as motion. National Geographic followed the controversy closely. In its detailed reports, the magazine revealed that most of the early NASA readings were inconsistent and could be explained by environmental interference, such as heat drift or magnetic coupling. In several tests, the supposed thrust shifted direction when the cables were rearranged, showing that even the smallest wiring detail could mimic motion. These flaws meant that every test showing thrust could still be traced to environmental noise rather than genuine propulsion. This skepticism is not stubbornness, but discipline. The conservation of momentum has been tested in trillions of particle collisions across every known scale of physics. It is as certain as gravity. To violate it would not only rewrite propulsion theory, but also tear down the mathematical structure of physics itself. That is why scientists remain cautious when faced with claims that sound like perpetual motion. Still, a few scientists tried to imagine how reactionless motion could be possible without breaking the laws of physics. At Plymouth University, physicist Mike McCulloch introduced what he called the quantum inertia theory. He argued that inertia, the force that resists any change in motion, might not be a built-in property of matter after all. Instead, he believed it comes from tiny waves of radiation that fill the vacuum of space known as the quantum vacuum field. When an object accelerates, these waves shift slightly, creating resistance. McCulloch suggested that if someone could control or manipulate those quantum waves, they might also control inertia itself. In theory, that could make an object move without pushing against anything. It would be a form of propulsion powered by the structure of space itself, not by fuel or exhaust. Dr. Burns's helical engine followed a different path. It did not depend on quantum fluctuations or vacuum energy, but on Einstein's relativity. His design didn't extract anything from the void. It stretched the definition of motion by exploiting the change in relativistic mass. Both concepts shared one dream: propulsion without propellant. NASA officially categorized these pursuits as high-risk, high-reward physics. Engineers understood that 99% of such ideas fail, but if one worked, it could revolutionize space travel forever. For skeptics, disbelief became fuel for stricter tests. For believers, it was motivation to prove everyone wrong. And that determination led to a series of quiet experiments that NASA engineers hoped would finally prove whether the anomaly was real or just an illusion. The tests that shocked NASA. After the controversy surrounding NASA's early EagleWorks experiments, the agency decided to try again under far stricter conditions. This time, the testing was moved to the Marshall Space Flight Center in Alabama, where engineers could build a more controlled setup than ever before. The goal was to find out if the strange thrust readings were real or just experimental noise. The new tests were designed. Every variable had to be locked down, every possible source of interference removed. The setup looked nothing like the early experiments at Eagleworks. The engine prototype was placed inside a vacuum chamber, an airless environment where friction and air currents couldn't influence the results. Around it, engineers built heavy magnetic shielding made of mu metal, a special alloy that absorbs magnetic fields. This prevented Earth's magnetic field, which is a major source of false readings, from interfering with the equipment. The device was suspended on a torsion pendulum, a platform so sensitive it could detect movement smaller than a human hair. To measure that movement, scientists used laser interferometers, which detect even the smallest deflection by bouncing beams of light across mirrors and measuring how they shift. The chamber itself was kept at a thermally stabilized temperature, meaning heaters and coolers maintained a constant degree so that expanding metal couldn't mimic thrust. Independent monitors from third-party labs watched every step through data feeds to ensure the results were legitimate. After weeks of testing, the data came in. There were minute, consistent thrust signals. They were tiny but measurable under isolated conditions. These signals were small, in the range of micronewtons, but they repeated often enough to rise above random error. In simple terms, the numbers were too consistent to be dismissed as coincidence. That discovery stunned the team. They had expected nothing. Instead, they saw a pattern that defied easy explanation. The findings quickly drew attention from other agencies. Both DARPA, the U.S. Defense Advanced Research Projects Agency, and the European Space Agency, ESA, began separate studies. They explored related theories such as nonlinear electrodynamics, which is how electromagnetic fields might behave differently under extreme energy conditions, and quantum inertia, the idea that empty space itself could influence motion. While no one confirmed NASA's data, the very fact that these groups were investigating showed how seriously the anomaly was being taken. Some of the readings even hinted at a strange effect called asymmetric photon recoil. Normally, when light particles called photons bounce inside a chamber, their pushes cancel each other out. But here, there seemed to be a slight imbalance, as if one direction produced a stronger rebound than the other. Physicists speculated this could relate to vacuum fluctuations, the constant microscopic jitter of particles in empty space predicted by quantum mechanics. If the engine somehow interacted with this field, it might be tapping into the energy of the vacuum itself. However, Dr. David Burns and his colleagues faced a brutal challenge: energy demand. Their calculations showed that even a tiny amount of thrust required around 165 megawatts of power, roughly what a nuclear submarine reactor produces. This made the engine impractical with today's technology. Yet, mathematically, it didn't break any physical law. It only demanded energy far beyond our current reach. The team emphasized that this was not faster than light travel, nor was it proof of a working spacecraft. What they had done was reopen the debate about how energy and mass interact at near-light speeds. Even if the numbers were small, space doesn't need much thrust. In a frictionless vacuum, a steady micronewton push could accelerate a probe continuously for years, eventually reaching extraordinary speeds. Then came the most unsettling idea of all. If these results were not experimental error, then maybe the reaction mass, the material something pushes against, wasn't missing after all. Maybe it was hidden in plain sight. Maybe the quantum vacuum itself, the supposed nothing between atoms, was providing the push. That single possibility that empty space could provide the push opened a door few physicists dared to look through: the quantum frontier. The quantum frontier. For centuries, people thought of empty space as exactly that, empty. But according to modern physics, space is anything but nothing. It's filled with what scientists call the quantum vacuum, an invisible ocean of energy that constantly churns beneath everything we can see. Inside this vacuum, virtual particles, which are tiny pairs of matter and antimatter, appear and vanish billions of times every second. They exist for mere fractions of a moment before canceling each other out. Yet their brief existence fills all of space with a restless hum of energy. Most of the time, these fluctuations balance out perfectly, producing no visible effect. But some researchers believe that under special conditions, this vacuum energy can be disturbed, creating a tiny measurable push. Imagine tapping a calm pond with a stick. The ripples you create aren't from the stick itself, but from the water it disturbs. Likewise, when strong electromagnetic fields such as the ones generated inside engines like the EmDrive or Burns's helical engine vibrate or compress the vacuum field, they might create a small but real reaction force. This wouldn't break physics. It would mean that the nothing of space is actually capable of pushing back when disturbed. This connects back to quantum inertia. In this context, the idea gains new weight. If electromagnetic fields inside experimental engines can disturb that same vacuum, they might amplify or redirect the minute forces predicted by quantum inertia. What was once a fringe theory begins to look like a possible explanation for the faint thrust NASA recorded. An interaction not with fuel or exhaust, but with space itself. Experiments related to this theory already exist. Physicists studying Casimir forces have measured the pressure that vacuum fluctuations create between two metal plates placed extremely close together. Even though the plates are in a near-perfect vacuum, they feel a gentle inward pull, as if the vacuum itself is squeezing them. That effect, though small, is proof that the vacuum has structure and that it can exert force. Modern research into vacuum energy extraction and Casimir-based propulsion now explores whether these pressures can be amplified or redirected to produce movement. Some scientists suspect that Burns's helical engine might unintentionally be coupling with this same vacuum field. In this scenario, the ions accelerating through his coil would generate electromagnetic waves intense enough to interact with quantum fluctuations. Instead of violating physics, the engine might simply be using a property of space we don't yet fully understand. The thrust, then, wouldn't come from nowhere. It would come from the quantum vacuum itself. This line of research has inspired a new generation of NASA proposals, sometimes called quantum drives. These designs explore how electrodynamic field asymmetry, imbalances in electric and magnetic fields, and even space-time curvature coupling could allow propulsion without traditional exhaust. Each concept walks a fine line between established physics and the edge of the unknown, challenging our sense of what impossible really means. History shows that such skepticism often precedes discovery. When nuclear energy was first proposed, it sounded like fantasy. When Einstein introduced relativity, even other physicists doubted him. Yet both ideas changed civilization forever. The same disbelief now surrounds quantum propulsion. If these principles hold true, the first engines to harness the quantum vacuum could open the universe in ways humanity has only imagined. Space itself could become the fuel. And that brings us to the reason this story matters. Not just for scientists, but for everyone who has ever looked up at the stars and wondered how far we can really go. Why NASA's quantum engine could change everything. If NASA's quantum engine works as its early data suggests, it could become the most disruptive breakthrough in the history of space exploration. For the first time, an engine would depend only on an external power source such as solar panels or a small nuclear reactor, and could, in theory, run forever. In the frictionless vacuum of space, that would mean a spacecraft could accelerate continuously, growing faster each second until it reached a significant fraction of light speed. No refueling, no payload limits dictated by fuel mass, just endless motion powered by energy itself. The first transformations would be immediate and dramatic. Deep space probes could keep traveling for centuries, sending back data from regions of the galaxy humanity has never seen. A single probe launched with a quantum engine could map thousands of star systems, crossing distances that once required entire generations. Missions that now take decades, like Voyager's journey through the outer solar system, could be completed in years. Even modest, steady acceleration would eventually build to astonishing speeds, since spaceflight is not about power, but persistence. In practical terms, the potential is staggering. Continuous low-thrust engines could send cargo to Mars, the moons of Jupiter, or even Titan without the need for vast chemical fuel tanks. Interplanetary transport could become routine, turning distant worlds into reachable destinations. At 99% of light speed, a trip to Mars could take minutes instead of months, while a journey to Alpha Centauri could take a few decades within a single human lifetime. That single shift would collapse the unimaginable scales of the cosmos into something navigable. Such a discovery would not just change travel, it would change physics. Every major leap in understanding, from Newton's laws to Einstein's relativity, has redefined humanity's place in the universe. If NASA's quantum engine is proven real, it would join that lineage. It would force scientists to rethink inertia, momentum, and even the structure of space-time itself. This is no longer about escaping Earth's gravity, it's about understanding how the universe moves and learning to move with it. NASA's message has always been the same. Progress begins where certainty ends. Every impossible idea, one engineer said, begins as a mistake we choose to investigate. With each new test, the impossible seems a little less unreachable, and the next great leap in human exploration may already be humming quietly in a NASA lab. What do you think about NASA's quantum tests? Comment down below.